Yes, we can.
Okay. Today I would like to tell you about the paper Synaptic Field Theory for Neural Network. And this paper was published in March 2025 by the group of scientists from Department of Physics of Korea Advanced Institute of Science and Technology. And in general, this paper is devoted to the consideration of weights and biases of the large neural network of the values of field in some specifically defined space. And if you have some scalar field, which is a scalar field, then we have some dynamics of this field determined by the Euler-Lagrangian equation from one hand. From the other hand, its dynamic should be predetermined by the dynamics of trainable parameters, such as weights and biases. So it's a very interesting paper, and I tried to explain the main ideas of this paper step by step. And let's start with the introduction of the neural network description and its architecture. The authors of this paper use a standard feed-forward network. So there are m-small layers. And here you can see a data set, so-called. X represent training inputs, and Y desired outputs. So I index can change within the size of corresponding input or output layer, and L is some specific element of the data set. So L change within the size of mini batch. Also, the authors introduce Z tensor, which represents the prediction of the deep neural network. And also, authors use usual activation dynamics. So H depict the value of neurons on the m+1 layer, and it is some linear function of weighted combination of neurons on the previous layer. So according to this dynamics, according to this function, the signal pass through the neural network. And sigma in general, in general architecture, is a non-linear function. Also, I would like to mention that Wijm includes all trainable parameters. So if we fix M, Wij represent all connections, all weights between two layers, and also biases. If we add for every layer some additional neuron, we can perform it in such a way. And then also authors use usual cost or loss function, which is a mean square error function. And neural network tries to minimize it, changing trainable parameters, changing weights and biases between all layers of the network, according to gradient descent method. And T, capital here, is a discrete step. It is a discrete time, but we can interpreted it as some continuous time. And then we will obtain the differential equation of such a form. And the main idea on this step is to find the Lagrangian of some mechanical system and find action, minimizing which we obtain such a differential equation. And also would mention that here should be all indexes. It's just omitted by authors of this paper and by me too for simplicity of notation, but this is equation for every trainable parameter. So we have a set of stochastic gradient descent equation, and we want to find corresponding set of Euler-Lagrangian equation. What then author do in their paper? They want to find action and Lagrangian not leading, not given these equations, but this one. So if we consider the limit of the equation on the left side, when gamma is much greater than 1 and this term dominate under this one, then we will obtain our desired equation. So it is so-called a high viscosity limit because this term in physics usually associated with some viscosity, with some dissipations in the system. And it can be shown that if we consider such an action, then we really obtain such equations of such a form.
So it's not really the limit of gamma greater than 1, it's the limit of gamma greater than second derivative of w divided by the first derivative.
Yes, it's correct, but it's from paper.
Well,
yeah.
You can improve it always.
Okay, thanks. Okay, we have anyway Lagrangian of such a form, and authors of this paper associate this factor with a metric volume element along the time direction.
Mm-hmm.
So it's some scaling factor along time. Okay, what is the main idea on the next step? The next step should involve the transformation from a discrete space to the continuous one. So we want to change the summation with the integration. And then we can associate W with some scalar field in the point of space. And you can see it here. So I associated with the X direction. Here should be J, here should be M. J associated with the Y and...
Have you been copying and pasting it?
Yes.
Guilty.
But yeah, if we have some specific indexes, we have some specific point in three-dimensional space, and we can choose a flat space, so coordinates we have Cartesian coordinates in this space, X, Y, and Z. Okay, but
maybe, Katya, the thing to mention in the previous slide is that this Lagrangian, which is inside of there, is time dependent, which is rather unusual, right? For usual classical mechanical problems, everything that's under the integration dt would be considered as Lagrangian, and that's time dependent, has this exponential, explicit time dependence, not implicit, but explicit, which is unusual.
It was considered to obtain this differential equation, but the Lagrangian is strange, yes.
Yeah. Mm.
Okay, but there is some features. Should perform the transition from discrete to continuous space, and then we should to change summation with integration. But in this case, C should have some specific form, so it should be the sum, the same sum of some terms. This also should include summation over these indexes. It is a first point, and the the second point is much deeper, I think, because we want to obtain the field which is local. So there are no higher order interactions, because we want to obtain something like in physics, and we want to have local field. And then in this discrete limit, the dynamics of specific weights should be determined by the weights in its vicinity. So if you have weight in some specific point in the space, its dynamic should be predetermined by only weights in this neighborhood of this point. And then we really can obtain desired local field, but it introduces some additional restrictions on the cost function. So it's possible in only some specific system, some specific architectures. And then we will consider the toy model where it's possible to construct a local field.
Not even architecture here, the loss function, right? The cost function.
And architecture too.
And architecture as well? Okay.
Yeah.
It's not clear yet, but
okay. I will demonstrate it further by this slide. It's about the changing of discrete space with a continuous space. Then if we can do it, we will obtain the action of such a form. And here it is an interesting result, because if we associate this factor with the metric volume element, then we can put such a relation between this constant and obtain de Sitter metric. So
well, the determinant of the Sitter metric, not the metric yet.
Yes, a determinant, positively defined determinant under square. Yeah. If we have such volume metric element of such a form, exponential form, it can be associated with de Sitter metrics. Okay. And so in this paper, authors established a duality between deep neural network and field theory with some scaling factor. So if we have such exponents here, then it can be interpreted as a stretching of spatial axis with time. Okay, but it is a general picture of the approach, but now I would like to demonstrate some specific examples, some toy model where it's really possible to construct local field. So let's consider very easy toy model where there are only two layers, input and output, and neurons on the second layer are determined by only nearby neurons from the first layer. So you can see connections on this picture, and also you can note that here there are periodic boundary conditions. So it is a specific architecture, and also authors use a linear activation function between these layers, and they use a usual cost function, just mean squared error. And also I would like to emphasize here that notation have changed, and now weights have only one index, but it's possible to write in the previous form. And then what will we have? We will have only flat space because m is equal to 1 and z is constant. And we also have one direction in the flat xy because there are all non-zero weights will be lay on this diagonal. So y is directly proportional to x. And we will have one-dimensional space. And then utilize this notation, we can show it. So what authors done in their work, they changed indexes, they shifted weights to get rid of linear terms in these expressions for every element of the sum. They want to get rid of the linear elements with respect to W. And it's possible to achieve it changing weights by some specific shifts. And the loss function will get such a form. So only quadratic terms now appear in the summation. Okay, if we're dealing with such a cost function, it's easier to perform the transition to the continuum limit. And then we will have such potential-like term in the Lagrangian. And then utilizing the general formula, we shouldn't forget about the kinetical-like term, and then we will obtain such action like here. And you can see that this Lagrangian in the brackets is local with respect to space-time point xt. And then we obtain, authors of this paper obtain the local field. But there is some problem because if we see into this Lagrangian in brackets, that it's not possible to represent it in the Lorentz covariant form. So there is a Lorentz violation here because of these x-dependent factors, k and j.
But can't you just absorb it into redefining, coordinates x? I mean, there is still freedom for you to choose metric for x as you wish, and for t as well. So, I mean, I would think that in 1+1 you can easily get rid of all those coefficients and make it completely Lorentz invariant.
Also, these coefficients k determine these coefficients k and j determine on input data, depend on input data.
Oh, x is not. I thought x was position. No.
X is position. X it is coming from this I.
Uh-huh. Well, generally, of course, you have to
do it.
Yeah.
Okay, maybe it's possible.
Well, you have to write, of course, this non-trainable variables there, which you're saying. Yeah, but then it's a field theory that you would have to have both W's and then something that comes from the state of neurons, H, what are they called, H? Okay, anyways, and I understand. Thanks.
Okay, and here you can see the direct duality between objects belonging to neural network and synaptic field theory. So weights associated with the field, training examples, with coefficients k and j, and they are like sources in the field theory. Indexes associated with the space, indexes A, J, M, discrete time index in the neural network associated with the continuous time in the field theory, cost or loss function with the action, but not action, but
Yeah, I don't think so.
I would say
Yeah.
potential form in Lagrangian.
Yeah.
Okay. And step size can be expressed through Hubble parameter.
But hold on, in this example, the sources, it's a one-dimensional example, 1 plus 1, right? So the
Yes.
sources are not really external in this example. They are internal. They lie in this one.
Yes, because only two layers.
So do they have examples where the sources are actually like, do you have, I think the minimal you have to do is something like 2 plus 1 if you want to have um, if you want to treat them as sources, as external sources. Did they have like 2 plus 1 dimensional, or one plus one was the only thing?
Maybe it's maybe interesting to consider not such a simple toy model with 3 layers, for example.
Well, I mean, many layers. The point is still, you're gonna still have this non-trainable variable states of neurons everywhere in the bulk. So you cannot really treat them as external parameters. They would still be like fields. They will be like fields coupled to W's. They're not external, and they're located. The states of neurons are located in every neuron, so they're located for all W's, um, which would be parameterized by at least 2 plus 1 parameter. But I guess I don't understand why they would call it external sources. It's probably
Okay, they called it so just because K and J associated with uh, neurons on the input layer. But how they give such a source interpretation, I don't.
no. What I mean, like if you add more layers, right? There'll be yes, the sources will still be on the left and right, input and output. But then there'll be a lot of dependence of the state of neuron in the bulk. And this would appear as some couplings to W's. And so you would still need this extra field-like degree of freedom, I think, in the bulk. So the model would be more complicated than that. But okay, I understand what you mean. Thanks.
So there are problems with locality in general,
Mhm.
but it's possible to find some specific architectures and cost function, some specific activation, cost functions, and so on, where this problem not doesn't appear. And also, authors emphasize possibility to apply field theory methods to neural networks investigation. So um, that is.
Perfect. Thank you. Thank you, Katya. See if there are any questions.
Yeah, so
Go ahead. Yeah.
when I started reading like the paper, like I just skimmed through it. I was expecting to be a little more closer to what the lattice gauge theory is, because that's what I studied. But it's really not like the space-time in the lattice. We discretize like the space-time, like that's a lattice. But here we are doing that with the weight space, right? That's the weights are actually kind of like the space that we're doing here.
Well,
That's
they
what
have
I'm
one
trying to
plus one
figure.
dimensional lattice, right? For
Right.
double.
In this case, yeah.
Now, if you want to see more dimensional lattice, you can check my paper. It's on the emergent field theories from neural networks. There you can get more. There is a little bit different notion of weights. Weights actually, what the role of weights and biases and states of neurons. But yes, I agree that there's still work to be done. Okay. Other questions, comments? Diego, I didn't cut you off because if you were going to ask a
No,
question,
I was gonna.
I just wanted to.
It was like the kind of question that's not really a question, it's just a trailing off comment. I
Or
think
comments. You
this
don't. There has to be
exactly.
no questions, like comments, suggestions, right?
It's more of a comment. Yeah.
What I found in this construction's most hardest thing to do is to get the Dirac field. So getting the scalar field is kind of easy. I mean, they've showed one example of how you can do that, but getting Dirac equation was harder. So that's my attempt on to deriving field theories from neural networks, but there might be others. Okay, other comments, questions, suggestions?
Hello, I have a question here.
Go ahead, Thomas.
I don't understand why do they use a linear function to the activation function. I mean, isn't the idea to use a non-linear function for sigma? And I don't understand and how would it be, how would it complicate the things to introduce a non-linear function here?
Good question.
I think that if they would consider some polynomial function, for example, if we consider some series for sigma, then they will have terms with a multiplication of different w's with different indexes.
Okay. Okay.
No, but
So,
I think you can still do the expansion perturbative analysis, right? So
yes, perturbative
actually,
expansion.
the one thing I
but
also was confused about, because in the beginning you said the function is non-polynomial. You wrote it, and then you
yes,
considered this
yes.
the linear function, which is polynomial. So I guess that was disconnect there. But
I agree. Usually, the activation function should be non-linear. Okay.
no, it's okay for it to be linear. But I think to address
But
Thomas's question, I mean, even if it's non-linear, very often you can do perturbative expansion.
non-linear for large neural network when there are more than two layers. But in this trivial model, it's possible to consider this function for simplicity of the final Lagrange.
I would actually say the following. So even if you complicate this model by adding more layers, right? Because the activation function is linear, you can just always collapse it into one layer.
Yes.
But then it would have maybe non-local interactions with respect to the cost function. But yeah. Alexander, go ahead.
Hey everyone. Yeah, sorry, that somewhat contradicts my understanding of a neural network as an approximator. As far as I know from other lectures, that's the point, to have nonlinear activation functions, so you are able to approximate. If you have only linear operations, including the activation function, then you have linear approximation at the end. Okay.
Yes.
Yeah. Did I get it right?
Correct. It's correct, but they have chosen a linear activation function just for toy model consideration, where there are only two layers, and this toy model cannot solve some
Non-linear problems.
non-linear problems.
No, but
Maybe
Alexander is right.
it
Usually
has
we
no
want
application, but it's just the simplest way to obtain a local field and simple Lagrange.
Yeah, so I think the objective was not to get a neural network that can be trained to do some useful learning, but to see what's the simplest one that can give you a simplest field theory.
So
But
it
of
will
course,
just give you a linear surface, a plane, right? In some
yeah,
point of space.
exactly. So it's not going to be very advanced. But yeah, I mean, if you really want to use some kind of field theory techniques to study a real learning system, then you have to add nonlinearities. You also need to add the depth and many other things that come with it.
They tried to consider some general neural network, but then
they stop trying.
they have come to the non-local field once
Of course,
again.
absolutely. Yeah.
Yes.
So, and that's why I think that there's this interpretation of field as being parameterized by I, J, and M will necessarily generically produce you a very non-local theory, which isn't a field theory. And so like this assignment of to I, J, and M as if they were coordinates isn't gonna do the trick. And perhaps the way to do it is to use kind of locality in the interactions that are mediated by W's, but have some kind of locality in X's, I think, in the states of neurons. But then it would be a constraint on the architecture. So yeah. So field theory will necessarily involve some constraints on the architecture, but the question is whether there are non-trivial architectures that you can get this way, and then we can use the methods of field theory to understand learning and vice versa. So that's kind of the general idea. Okay, are any other questions? Comments? All right. Well, thanks everyone for coming. Thank you, Katya, and I'll see
Thank
everyone
you.
next week. Thanks. Bye.
But